Okay, now this is a fairly old study. It was done on a sample on a product that was from Western Canada by one of my graduate students, but this is like 12 years ago we finished this project. This deposit of kaolin is on the surface. In fact, the area is called the Whitemud area, so the product was called Whitemud. They have 175,000, or sorry, million tons on the surface of, sitting on the surface of the ground there, and or slightly below ground in some cases. And they built a plant right next to it to mine it and dry it and calcine it. And they built a plant with 175,000 ton per year capacity back in 2000. And it was open in 2007 or 8. It's a bit off-white. It's but it has about 20% quartz in it. It's not pure. It's in the order of about 80% pure. Although I think later on they were able to remove more of the quartz. The sample we have dates back to when it was there. In case you wonder where it is, this little map on the left here. Let's see, pointer. Where's the pointer? There, shows where it is. It's just north of the U.S. border in southern Saskatchewan. And it's a fairly rural area, so there is railway transport, but otherwise it's pretty isolated. And it's either at the surface or just below the surface. In this case, there's a ball clay on the surface. There's a coal seam. There's coal in this area too. And immediately below the coal seam is the kaolin ore, which they mine. So they can visually see where the kaolin starts. And then they take it, they dry it, and then they run it through a rotary kiln to turn it into metakaolin. And so the test program we did at the time measured physical properties of concrete and also a bunch of durability properties, including sulfate resistance, chloride resistance, a de-icer scaling, and alkali-silica reaction. Now, the sample we have, you can tell it's not pure because it's only about 30% alumina. Whereas a pure metakaolin that we've done research on earlier, a fairly high-grade metakaolin, about 45% alumina. And so you can see the silica is higher because of the quartz impurities. And we tested a lot. We also tested ternary mixes with the slag cement from Ontario because they were talking about bringing to Ontario. And this was a commonly used SCM slag in Ontario. So we did concretes at 0.40, water binder ratio in 0.5, fewer mixes at 0.5. And we looked at 35 slag, 10, 15, and 20% of this metakaolin, and a ternary mix of 20% slag and 15% metakaolin. And we did our ASR and sulfate testing at 15 and 30% replaced. The fresh part, they're all air-entrained concretes because we live in a freeze-thaw environment in Canada. Our target air content's 6.5 plus or minus 1.5, and so these are all within that limit. There's some variability. The slump varied a bit at the top with the ternary mix and the 10% because we didn't have time to go back. We didn't have enough material to go back and repeat that. And you can see that may have been due to the higher polycarboxylate water reducer dose that was used in that study. We measured setting times. The Portland cement is this light, is the blue diamonds here. And there's so the slag was pretty much the same in terms of setting time. Initial and final set is the Portland cement, but the metakaolin mixes were faster by about half an hour or so. The ternary blend of slag and metakaolin, on the other hand, was slower setting time. But that may have been due to the higher dose of the polycarboxylate. May have delayed the set there. The strength development was good. What you see here is the early strengths of the 15 and 20% metakaolins at 1 day and 3 day exceed that of the Portland cement control mixture by quite about almost 1,000 psi or 5 megapascals. And then its strengths continue to rise over the time frame up to about 4 months here in this case. The ternary mix was slower at early age, but again, that was probably due to the higher dose of admixtures and higher air content. And so, but they did catch up at later ages. And just the strength for the 0.5 mixes You see the 15% metakaolin had the highest strength gain curve, followed by the slag mix is in red, the OPC is in blue. And the ternary mix is that purple one. Okay, we measured drying shrinkage according to ASTM 157. And we got less shrinkage, less drying shrinkage at 28 days with increased metakaolin, and that continued on to later ages, just not showing it. So the cement had the highest drying shrinkage. We have an optional drying shrinkage limit in Canada, in the CSA standards, 0.04 at 28 days. We measured sulfate resistance using ASTM C1012 mortar bar tests. We did them in two types of sulfate solutions. And what we see here is that there's some other mixtures in here besides this that I'm not talking about here, some flash mixtures. I won't talk about them. But the Portland cement mixture was this red line. It failed before 6 months, so it wasn't sulfate resistant. But all the ternary mixes and the ternary mix and the 3 metakaolin doses all passed at less than 0.1 at 12 months. If we carry that out at 18 months to match the ACI 318 option 1 for S3 exposure requirements, the mixtures pass with the exception of the 35% slag at 18 months. Sorry, I got ahead of myself. And in magnesium sulfate, we got very similar results. The metakaolins did very well, and the ternary mix did well. Did better than the slag at 35% replacement. The only thing we did notice is that in magnesium, they both passed magnesium sulfate and sodium sulfate. We did notice that there was some slight surface scaling on the bars with the magnesium sulfate that we didn't see in the sodium sulfate. We didn't see any damage in the sodium sulfate. In more recent tests, for part of the outdoor exposure study that we did more recently, we tested the same metakaolin 15% in concrete and put it in long-term sulfate storage underground, and also a mixture of metakaolin and slag. And they are performing better than type 5 or sulfate-resistant Portland cements at this point at about 4.5 years. These concretes are now 11 years old. I just haven't been able to measure them recently because of the COVID restrictions on our field work. But this is documented in a PCA report that Mike Thomas and I wrote in 2016 on sulfate resistance of Portland limestone cement concretes. 1202 ratings, other people have shown 1202 ratings, and you can see that as you increase the metakaolin, the 28-day coulomb ratings go down significantly, and they get better with age. The ternary mix was similar to what we would get with a 15% metakaolin. So the slag, so it's 15 metakaolin, 20 slag. And we see that, of course, water cement ratio had an influence. I'll leave that given time. We also measured the ASTM 1556 apparent bulk diffusion, and you can see that the bulk diffusion rates at 0.40 on the left and 0.5 mixes from the right. We tested them at 28 days of age and also at 4 months of age, and you can see that the metakaolin mixes are good. Ternary mix is even the best one here at 28 days and on 4 months. So they're getting better with age, and all the metakaolin mixes had low chloride diffusion relative to the Portland cement control, not surprisingly. So this thing's moving ahead on its own. Our best performance was a 15 or 20% metakaolin in the ternary blend with 20 slag and 15 metakaolin in both these test methods. And we did concrete prism testing for 2 years using ASTM C1293 with 5.25 kilograms of alkali loading. And you can see that the one that failed I put in pink, that's the Portland cement controls, a high alkali cement. And all the mixes with slag or metakaolin or the ternary mix all passed the limit. The 10% metakaolin was just on the limit, just below the limit of 0.04 at 2 years. So you might think that's a bit too close to the line. And so 15% and 20% certainly were very effective. And that just shows the expansion. We measured them out beyond 2 years. They'd pretty much stopped at that point. Now, the other thing we do is de-icer salt scaling. And this is a modification of the ASTM salt scaling test. The main difference is that we use sodium, the OPS is the Ontario Provincial Standard our highway department uses, that they use 3% sodium chloride solution instead of the 4% calcium chloride solution that is used in the ASTM methodology. And they use a mass loss criteria of has to be less than 0.8 kilos of mass loss at 50 cycles. Now, this test method has been problematic for concretes made with SCMs in the past, which is one of the reasons we developed a different Canadian standard test method. And you can see here that that's what happened here. The Portland cement, of course, doesn't scale. The 35% slag just hit the limit at 50 days, but all the mitigation and the ternary mixes all scaled to high scaling loss numbers. And you can see I've just shown a couple of them there. You can see the coarse aggregate exposed. The surface paste is gone, but after that, they pretty much stopped. So it was just somewhere between 10 and 25 cycles had this increase in scaling. And it may have been, it's hard to know why that is. They were finished with a steel trowel without some mistake. We should have just used a wood trowel. We may have trapped bleed water. We don't know about this particular admixture that we use for air-entraining, if it's compatible with mitigation. And as I said, we adopted a new test method in the Canadian standard after that, this C1293C, that has better relationship to field performance and scaling. And unfortunately, this work was done way before this test method was available. So we don't have scaling results for that to check on that. So the conclusion from this somewhat old dated study is that even with this impure source of metakaolin, as I said, is only about 80% pure. When used in 15 or 20%, doesn't impact set times much. It increases strength even at early ages relative to Portland cement. It decreases drying shrinkage, increases sulfate resistance, increases chloride penetration resistance, mitigates ASR, certainly at 15 or 20%, and appears, but unfortunately, it appears to be detrimental to in terms of the scaling test that we used at the time. And if we had more material and a new student, I could do that again, but we hadn't got that. So I'll conclude with that. Thank you.
So thanks,